So let's go ahead and get started with where we left off on Wednesday. Uh, we didn't cover this in any amount of depth that I think it probably deserves, but it's really meant to be just an illustrated example of the power of what you can do when you have these kind of self-referential pointers within your structures. This is just one example of what one can do by basically pointing to objects of the same type within the structure itself. And this can allow us to create more advanced data structures. One such example is referred to as the linked list. That is similar seemingly to what we had with the vector type, where we can dynamically shrink or grow using those memory allocation functions. The main difference, the main advantage of why we would want to use a linked list is we're not limited to saying allocating a block of memory as an array at any one given time. By setting up these pointers explicitly, what we are really allowing us to do is to say, this node in the list can be located at some arbitrary location, this can be located in some arbitrary location, and we can traverse the list. We can effectively iterate through the list, no longer using that array syntax where we do vector of I and vector of I plus 1, etc., but by following these individual next pointers. And our for loops will look a little different because of that. And this is actually would be a very common type of programming style that you would use as you start to develop more advanced programs, not in this class, but more likely in follow-on projects in class, where instead of iterating for I equals 0, I less than n, we're actually starting with a pointer and we're updating the pointer as we go. Follow that pointer to get to the next element that we have in our list. That will allow us to do things that at first blush look very similar to what we already could do with the vector, meaning inserting an element or appending an element into that list. But because now we no longer have to have these located in any particular consecutive locations in memory, doing that insertion is going to be a lot more efficient. Maybe not for 20 elements in a vector versus a list, but 20 million elements in a vector versus a list. So we're gonna dive through that example, and once we finish it, that's all we really need to cover for today. But this example that is on Replit was really meant to serve two different purposes, and it wasn't doing a good job with either of them based on the version that I had on Wednesday. So I went in and cleaned it up a little bit more and added some comments, and you can use this as your starting point. Because it was meant to illustrate both this linked list concept. So we're still gonna have a linked list. We will get to that. That is relevant for what we'd like to do. And it's also meant to illustrate how one gets started with this curses library for more fine-grained control of effectively printing things to the screen. Some of Lab 8 is using that curses library. A lot of your projects will likely want to use the curses library. Depending on the nature of the project, you may choose for that to be in your rubric to be either required, expected, or potentially bonus, depending on how you've structured your rubric. But I think unless you're doing something more advanced than that, for almost all of the projects, it's likely you'll want to start with the curses library versus trying to get things to work perfectly right using a bunch of really carefully constructed printf statements. Hopefully through this example, which I'll try to walk through a little bit more slowly than on Wednesday, I wouldn't say we'll become experts in curses, but we'll have kind of the recipe to get started. And from there, it's really just a matter of looking up what these particular functions do and what the options are as we get started with curses. Let's start with main then in this example. Actually, let's start before main. When we want to get started with curses, there is a header file and there's a library associated with it. Header file is just called ncurses.h. If you Google that, you'll get all sorts of different advice. It is system dependent. For us, including ncurses.h will work for our purposes. With our Replit environment that we use, where we configure our packages via that Nix package manager, to actually have access to that curses.h, you want to explicitly say, in this project, I want that ncurses package. So for your project, you can copy that file over, or you can just include that line here. So that's the first part. There's then a series of setup functions we typically call once, and a series of cleanup functions we then typically also call once at the very end. Setup, and this is my own function, we could call it whatever you want, is to get the terminal in the exact state we would like it to be. Cleanup is to get the terminal generally back to the more default state we would use for our printf statements. You can actually do this without the curses library. Things like changing the color of how our font is being displayed. We've played around a little bit of that using sort of these control codes. The whole point of the curses library is to provide meaningful wrapper functions for that functionality, so you're not just kind of hacking things together. So in your curses setup, which you would call just once as you jump into main, you would be then configuring what you want your terminal to look like and potentially checking for some things. One function is just initial setup. It's called the knit screen. There's this concept of a screen in curses, which while it's still using this shell or this terminal kind of environment, is a little bit more analogous to kind of the GUI view of the world, where you can have multiple windows, you can create menus within those windows. You can do those for your projects. It may not be necessary. It does depend on your project. In this case, we're saying just initially set up the screen. There's a whole series of options for configuring the various features of curses. I've just included the ones I think will be probably pretty sane defaults for a lot of your projects. This one, cursor set 0, don't show the cursor. Don't show where the cursor is currently located. It's possible you want to show the cursor, but in general, if you're using it for keyboard style input to a game or something, you probably don't want to show the cursor. Raw mode, if you really read the documentation for what raw mode is doing, it's not providing any initial processing. I was trying to find, if I click on that, it's listed here though. Not provide any additional processing on any of the keyboard inputs we are receiving. There's a couple other options that I'll optionally turn on later. No echo can be a useful mode, but it depends on what you're doing with your keyboard input. As it sounds, that's saying when a user types in the letter A, don't actually show that the letter A got pressed. You actually are using A as an input to your program. So those are the style of just setup functions. They're pretty consistent across a lot of our applications, so it kind of makes some sense to say, wrap them in a function, call that function at the very beginning. For at least now, call endWin is the other function when we're ready to get back to our regular terminal. In case your program is messing around with things like color and echo, if you don't end that configuration, when you go back to your terminal, it won't actually have changed back, and that may or may not be a problem for how you're running your program. That's the first part, the setup and then maybe the cleanup. Then there's going to be this main kind of event or drawing loop, which is common across all sorts of sort of graphical libraries you may want to have in your program. But for curses, if we're going to use it in that kind of mode, it is very common for there to be kind of an infinite loop, our main kind of listening or control loop here that we have here, which is going to be taking user input and using that to control and change what is being drawn on the screen. It should generally follow this basic loop format. This is not to say that every program has to look exactly like this, but you have to reason about what you want your loop to look like if it's not to be like this. We start with erasing the screen, which does exactly what it sounds like. Clear what's currently being displayed on the screen. A series then of draw calls, that's kind of the graphics library phrasing for it, or printf type calls. A series of calls, in this case there's just the one, that is to put something on the screen at one point in time. In terms of how we do those printing calls, they're very similar to calling printf and includes a lot of the functionality one would expect of a printf call. The main difference is we can be more explicit and say, do this printf and do it a particular XY coordinate or row column coordinate on our screen. In this case, because I wanted a wacky looking program, I just set up a random value for those row and column values here. You probably don't want that. You want to print something in a particular location, but just to show that it does something, that's what it's currently doing. Randomize a row integer, randomize a column integer, and then have a call that actually does a print. At that location, print hello world. I was intentionally messing around with this. Quite a few of your projects may want to do some of those Unicode characters, and that's fine. Printf, at least in Replit, supports that. This MV print W also supports it. You can think of that as print window if you want to think of what the W stands for here. To support Unicode, for reasons that I have tried to really understand, but have been okay with just knowing that it's necessary, there's an additional function you have to call first. If you call that function and you don't use Unicode, your program still works just fine. So we set the locale of how we're supposed to interpret various character sets in the beginning of our setup, and then we can print things like Unicode characters in our MV print W calls. So our main loop is erase. Yep, sure. It would, and you know, it's kind of a pain. We did that with a couple programs earlier in the semester, but we didn't really think too much about it. If you wanted this to be like a variable, right, that we wanted to store it as opposed to like having it kind of hard coded in there like anything else, right? You can do that. So although it doesn't seem, and we should be able to do that. You see that syntax I have here, and then now we could choose to do, and I'm happy to do so. You know, %s, %s, %s. Well, you don't need it. Usually, don't want the new line here. Cherry, because it is not. I don't know why it's complaining here. Should be okay. Nope. I don't trust that that's not Replit just being difficult. It supports Unicode. It obviously doesn't support it as well as it supports just kind of native code here. Yeah, it's fine. That's Replit getting confused about having Unicode, but it should be supported. So it's not a single character. That's the first answer I was getting to. We haven't covered Unicode. There's a lot to cover. We're not going to cover it any more than this, to be honest. Unicode is a multi-byte representation for these advanced non-ASCII things. Unicode characters can be 1 byte, they can be 3 bytes, they can be more than 3 bytes. You can't easily tell in looking at it how many bytes it is. Cherry Unicode character. I mean, I'd have to look it up. I have no idea what it is. The random website hopefully is acceptable. I haven't checked this. Unicode character Cherry. I hope that has no implications either. I meant nothing by it. If it does, I apologize. I didn't mean anything by it. This is from the Pac-Man game. In this case, again, there's a lot you have to kind of read between the lines here. That Cherry character is actually a 4-byte character. You have to kind of take my word for it, but it's showing the 4 bytes that it has here. So if I were to instead say this is just a single car, that should be a compile error. The nice thing about that open bracket syntax is the compiler is smart enough to tell us how large it is, so we don't have to worry about the length, but it is 4 bytes long. Once you do that, I can actually run it and confirm that it actually works, and it's, you know, it's okay. It does print it out as expected. Did that kind of, yeah. It would be a random byte. Oh, we could have some fun with this. I think what they tend to do for like compatibility with the original ASCII table, I'm not an expert on this, but this is my best understanding of what happens in this case. To be compatible with the original ASCII table, which we can open up as well, just really quickly here. That one should be a link I would have visited on occasion. We'll let Google figure that out. We'll come back to that. ASCII characters, the usual standard ASCII set is 0 to 127, right? So, or 0 to, what would that be? EF hex. Who needs the internet? Not me. Yeah, if we look at the hex row here, 0 to 7F hex here, 0 to 127. And so I think for that reason, to support kind of existing compatibility with the original the ASCII table, most of those Unicode encodings will be larger than 127. So if I instead tried to print out the Cherry as, and I feel terrible, are there other choices we can do instead? Let's do a more boring Unicode symbol. If I were to try to print that out as individual characters, syntactically it should work. Instead of this, if I wanted to do %C, and for that to work, it'd have to be like Cherry of 0 or something. That'd be printing out 80 hex, or excuse me, F0 hex in ASCII. That shouldn't correspond to anything printable. So there should just be 2 cherries and maybe like a space or something that it printed out instead. So usually we don't need to know the actual encoding of our Unicode. We just have to be aware that in fact, it is not a single byte. It is this wider character. It is multiple bytes. And consequently, you have to treat it closer to a string. And functions like printf can already support those implementations of it as a string. I kind of agree, though, that in terms of like, writing scriptable code, this approach makes more sense than kind of hard coding those things in there. So if you're doing Pac-Man or something and you want to display the ghosts, you would have a ghost define, and then you would display the ghost at a particular location at a particular point in time. I appreciate that. I guess part of the limitation is there's a lot of Unicode symbols and a lot of different ways of encoding it. This method treats each of those as individual bytes. That's why it winds up, even though we think of it as a single character, it's not a single ASCII character, it's multiple bytes, so we treat it as an array, and then everything kind of sort of works the way one would hope afterwards. Going back to our main end curses loop, and we'll get into the linked list here as well. We erase, we have multiple or one draw call to put something on the screen, to put something in our terminal. Then the actual call, this is the part we didn't get right on Wednesday, we're kind of queuing up all these print calls, and then I don't think it's a great name, but refresh is basically saying, now execute all those calls. Actually draw all the things we requested you to draw, and we were missing that line, and that's why the screen was blank at the end of Wednesday. So have one or multiple draw calls, then actually draw what you've been queuing up, and then depending on what your needs are, read from the user, read some input character from the user, or sleep for a certain amount of time, and then just continue that sequence. Other feature that it does depend on what your particular application is going to be is to have blocking versus non-blocking I/O. Kind of a technical topic that you would learn more about in an operating systems class, but from our perspective, blocking means when I want to read in user input, the program just sits there and waits. Scanf is an example of that. When I have a scanf call in my program, by default at least, the program sits there and hangs until somebody types something in and presses enter. It's blocking. It blocks the progress of the rest of the program. Oftentimes, that's what we want. We want a user input. We don't want to do anything until the user has actually inputted something. If we were making an interactive game of some sort, Pac-Man's a good enough example of that, right? That one team is doing here. We don't want that. We don't want the whole thing to freeze until a user has typed in an arrow key. We want everything to keep going, and we want to be aware when the user typed in an arrow key, but we don't want to stop the rest of the program. That's referred to as non-blocking I/O. Keep the program running, periodically poll for whether or not a user has typed in a keystroke or not. In this case, we can kind of tell just looking at it that this is in a blocking I/O mode by default. How can we tell this? Because we have our infinite loop here, our while loop, which is erase, print out hello world, cherry, 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 and again, I didn't mean anything by that. Print out hello world at a random location. I'm going to change that Unicode character before we're done today. Draw the screen, wait for input, and continue. But it isn't doing that, right? It's not drawing something at a random location. It drew one thing at one location, and so when I press quit, it exits. So clearly right now it's in blocking mode. An aside on that as well, this is, Replit having recently kind of changed that console tab and how it runs things. For curses applications, I think you're going to be better served by running things in the shell instead. So unfortunately, that button, green run button, won't do what you want, but usually our applications are named main. We type /main. It gives you a bigger kind of default terminal size. I think it's going to be a more consistent experience as you're testing your applications, but yes, you'll have to remember the name of the application and type it in each time. So this I/O is currently in blocking mode. That was part of our setup, where I commented out, but if you want to have non-blocking I/O, I wouldn't worry too much about why specifically it's called this, but in terms of just our recipe that we want to keep using for our applications, we call in no delay, which is don't delay on our requests for input. I'm going to stay within the shell. For me, it's always going to be make with our make file, and then I'm going to want to run the application. So you can kind of just remember make, next command, run the application. It'll do both for you. And now we get our kind of happy dancing, hello world. Because now it's non-blocking I/O, right? It's still calling that function get character, but it doesn't sweat it if it doesn't actually receive anything. Okay, moving on. Moving on to the next iteration of the loop. There may be a little bit of latency in this mode in terms of when do I hit the character, how long it takes to process it, depending on how much you sleep each iteration. That is a little bit of a challenging thing to handle in a C program that doesn't have really good asynchronous callback functions, but still it should be reasonably responsive that if I hit Q, it should still exit the program. Maybe it's 100 milliseconds later because I'm sleeping every so often for 100 milliseconds, but that's probably okay. We're not building a 60 frame per second first-person shooter in curses. I think we probably could, and it'd be really fun. But unless you're really up for it, we won't do that. And the I/O part of it will be the awful part of that application. Other curses example or questions before we kind of dive into the linked list version of this program. So instead, let us print out our linked list or build up a series of functions that will allow us to print up our linked list. So a lot of this I don't really have to change. So let's get rid of that stuff for now. We will want to have a function like before that prints out our data structure. We would call it something like print list or list print or something like that. Whether you put the erase and refresh call inside your print function or whether you leave it outside of your function, it doesn't really matter that much. We then also would need some functionality that actually builds up the linked list as we have here. And we have to declare a variable of that type. It's a structure that's just going to include an integer. So you can call this an int node because it's storing an integer in each node, and it's going to have a pointer associated with it. So we need to have some function that allows us to maintain a sorted list, right? To insert or append something onto that list and to maintain it in some sort of sorted order along the way. This is going to involve some pretty tricky, pointer arithmetic here. Try to go through it slowly, but I think this is only helpful if you're kind of engaged with this and maybe asking questions along the way for why this potentially works. I'll start with a couple of prototypes that we may want to use. There's a whole number of functions we may want to support, but at the very least, we're going to want to have a function that allows us to append something to the end of an existing list. This function is going to take an existing list, which we're going to point to via a separate pointer that is called the head. There is oftentimes, especially if it's a doubly linked list, an additional pointer that points to the tail, that points to the end of the list. For this case in which we're only going in one direction, having just a separate pointer that points to the head is something we're going to want to keep track of. So this function would then take that head as input. It is a pointer. And then if we're going to add something to the existing list, we're going to append some value, just some arbitrary value. It doesn't really matter what that value is. We are also going to potentially want to have a function to maintain some sorted order that allows us to insert a value into the list. And how we do that insertion depends on what kind of sorted order we actually want to keep track of. And then we're also going to want to have a function that allows us to print this out, and we'll use curses for that functionality. It was called list append, so we'll call this list print. This doesn't take or return any values because it's just our print function, but it takes that input as that starting pointer. So in a sense, I want to go back to the visualization of what we're setting up here. In a sense, there's two different things going on with regards to these pointers. You have the individual nodes that we're going to be setting up. That's going to use dynamic memory allocation, just like in our vector example, except we're going to kind of allocate it one at a time, most likely here. When we do so, we have to make sure we initialize those pointers to the right locations. Separately from that, we're going to have a pointer that points to the beginning of that list. It's going to store an address that just allows us to determine where is the beginning of this list. Actually, in the code example on the slide is not how I was planning on doing it, although we can also do it that way. I would argue probably, we could do curses set up first, or we could do data structure set up first. It doesn't really matter here. But somewhere we have to declare that we want to have a variable of that type. That is going to be the pointer to the head of our linked list. I kind of trust at this point the replit environment to initialize that for us, but for now, let's initialize it to a null pointer. to be explicit and say, we will have a head of a list, but it's gonna, so far it doesn't exist yet. It's not pointing to anywhere valid. Think of null as 0. Null is also a pretty clear signal in your program that that pointer is not pointing to anything valid. We could initialize it to some arbitrary thing, but that's probably not good coding practice. We're saying we have this pointer, so this memory gets allocated. There's an address stored in memory now, or a space for an address of a pointer to be stored in memory. It just points to 0 right now. Our key only opens up mailbox 0, and when we try to access that key, the mailman gets very unhappy and our program crashes. So we start with our head pointer, and the way I prototype that function, we're going to want to update that head pointer by calling the list append function to start with. Kind of like our dynamic memory reallocation functions, takes both the pointer to reallocate and returns a pointer. We don't have to overwrite the same pointer, but it's very common practice to reallocate and reassign that same pointer. List append, take the head, also take some value. I don't really care what value, some arbitrary 3-digit value. I haven't really thought about what values we want to actually have in our list, but some just arbitrary 3-digit value we're going to insert into that function at that point. If it's the very first one, we could also be just explicit and say we're going to append something to a null head, but now it's already initialized to null. We're going to append it to that currently blank head. And then at some point inside this function, we said if key equals q break, we can also say if the key is equal to a, we can call that function again. Append. So we have to have something in our data structure to start with. So let's put something there to begin with. And then as we go through our infinitely printing loop here, if someone types in the A key, append something to that. We're also going to be writing that insert function. So let's say if the user types in I, we're going to call that instead. And just for some arbitrary value, we're passing into that list to be stored as the integer. We could also do the remove function. I think insert and append is probably sufficient for now. And inside our steady state here, we're going to be calling list print. You could then argue that the way we have set this up, where we're printing out the list, and only if someone types in I or A does the list change, I would argue that we don't need to have the non-blocking I/O, that blocking I/O will work for our purposes. The downside of having the non-blocking I/O when you don't use it is you may kind of see the redraw and some flicker on the screen. It may not look as good as if you have the blocking I/O. In this case, there's nothing new to print because we're not randomizing anything. We're not putting a new location until someone types in something interesting. So we might as well wait until someone types in something interesting. So this would be user input. We don't proceed until we've gotten valid user input. That makes some sense because here the program doesn't have anything to do if we don't type in I or A or Q along the way. But otherwise, the curse's event loop is still the same. Erase the screen, print what you need to print. I know we haven't written that function yet. Actually execute the draw calls. So draw what you wanted to print with those mv_printw calls. Read in user input and change program state accordingly. If you really wanted to abstract that a little bit more, you'd call a function, call it something like read user input or something like that, and then use that with a switch statement or something like that. If we're only typing in I or A or Q, a series of if statements is probably sufficient for that purpose. So we have these 3 functions that we have to implement. I have the prototypes up there. We can start on the implementation. For print, that will probably be the easiest one once we've done these first 2. Let's at least get the bare bones of them up and running to start with. So for this one, we have to return something. So let's at least declare something of that type. And for now, this would be a definite bug, but we can just return it just so we have something that is in place and not invalid. Same for list append. We can do the same thing. It's going to take that head as input, it's going to take that value as input, and it's meant to insert or append at the end of that list that particular value that we provided as an input as a new node in our linked list. So let's think about that. We actually do need a new node. So append a new node with value, that's the name of the variable in both cases, with value at the end of the list. So we know we wanted to have a new node. So maybe calling it new node or is better than calling it node. I mean, it's fine. New node. We need to create a new node. What function will allow us to allocate memory for a new node? malloc, absolutely. 3 parts of the malloc call. I like to start with just remembering, yep, that's going to pass a pointer of the type we're requesting. So that's the casting part. There's the actual call to malloc. And then when we call malloc, we're specifying how many bytes do I need. It's a little different than how we've been doing it before. Here we're allocating a singular new node. So how big is that new node going to be? Just 1. And if you want to be explicit, because this looks a little different than our other usage scenarios, you can do 1 times that. That's not wrong. I mean, it's just you know, a little bit unnecessary, but the compiler will take care of that for you. I want 1 new int node, which will give me space for a value, will give me space for the next thing it's going to point to. We can then start to initialize that. We have a new node, it's a valid pointer. When I want to update the value to the value that's being passed to this function, new node is a pointer. How do I get the component called value from new node? How do I reference that? What new operator is required for that? Not the ampersand, not a slash. Okay, you're kind of pointing the right, I mean, okay, yeah, okay. It's the arrow, right? If it was not a pointer, we'd use the dot operator to get that component. And I talked about how syntactically it is valid to do reference pointer, then follow pointer, then use the dot operator. But more likely, more commonly, and more appropriately, what we use to grab the value is to use that arrow operator. The value is the value we pass in this function. You know, if that's annoying, you know, we don't have to call it value because it sounds ambiguous even though it technically isn't. We can call the input to this function new value. That just, maybe it makes it a little bit easier to kind of separate concerns, although technically it's not, from the compiler's perspective, not ambiguous. We're going to pass in new value. That's the value we're going to update in that value component in that new node we have allocated. Each node has a value. It also has a pointer to the next thing. This is going to be placed at the end. It's appended. It's going to be at the end of our list. So there's nothing for it to point to. But initialize it anyway. Initialize that pointer to null. Where do we actually put this though, right? It depends on what we get as input. And it looks like there's going to be potentially 2 scenarios here. One scenario would be if head is null, we have an empty list already. There's nothing there. We haven't allocated anything. It's the very first thing we're allocating here. We can explicitly check for that. So if our head is null, and you can just explicitly check that, if the thing we've passed to this is null, well, in a sense, we're done. Our head was null. There was nothing there. Well, okay, we just created something. That's going to be our new head. Let's go back to how we called this, at least that very first time we're going to call this in the program. Start with a null head. Give me a new element on that list. We pass in null. We check if we passed in null. And we already allocated a new node. That is what's going to become our new head of our list. Otherwise, if that's not the case, and you can do an else statement as well, but since you've returned, you really don't need the else. The control will end in this function if we get to line 43 here. Otherwise, find the end of the list. We don't know how many elements there are on the list. we have to get our way to the end of the list. If it was a doubly linked list, we'd have a separate tail pointer. That would make this a little bit more straightforward, but make everything else more complicated. So we'll stick with just the singly linked list. It's not null. We have a bunch of stuff, or at least one thing in the list. How do we know we've reached the end of the list? We start with head. We go to the next. We check that one. We go to the next. We check that one. We go to the next. We check that one. We go to the next. If we have set this up appropriately, eventually we'll get to a node for which the next is not pointing to anything valid. And that is how we would have to iterate through our list. So while it would be nice to do, for int I equals 0, I less than n, I plus plus, this is not an array. We can't do that. They're not guaranteed to be next to each other in memory. We have to follow these pointers side by side. Anyone who does C++ programming will see some version of this code, but we can do it in C as well. Instead, we really need to declare and allocate some sort of iterator for this, a pointer that we can update. So it's a pointer to that type. I don't want to call it I think that's misleading. We'll call it list iterator. This is going to be our list iterator. We're going to iterate through those pointers. We're going to follow all those arrows. Well, where do those arrows start? Starts at the head. Initialize it to that first arrow. Continue while its list iterator is not null. And then how do we update it? It's not plus plus, although that's tempting. It's update this guy such that it is now pointing to the next thing. Start at the head. Stop once you reach null, because that's how we know we're done. But continue on by updating the value of that iterator. Originally head points here. Update that iterator to point to the next one. Next time through the loop, update the iterator to point to the next one. Keep going. Stop when there's nothing valid to point to. Stop when the value is pointing to something null. That is going to be your advanced data structure kind of for loop. They're all going to look something kind of sort of like that. Instead of just an integer, you're going to have an iterator. And that iterator is just going to be following the pointers. This is a pretty common coding practice you'll see in C and C++ programs. We start at the head of a list or of any data structure. We follow pointers until there's no longer any more pointers to follow. And we want to find the end of the list. When have we found the end of the list? When that next is equal to null. We're on a node for which it's pointing to nothing afterwards. Instead now, I wish I'd drawn one more arrow on this slide pointing to nothing. We've gotten here, we're at the very end of the list. It's pointing to null. Instead now, we've allocated a new node. We're appending a node at the end of that list. Instead of pointing this to null, point it to that new element we've just created on the list. We've reached the end. Update, it was currently pointing to null because it was previously at the end of the list. What should we set list iterator next to if we've reached the end of the list? That would be nice. And if we talk about like doubly linked lists, we're doing a lot of that. In this case, we're only going in one direction. So we're following along. We got to the end of the line, but we've actually created a new thing to become the new end of the line. We just need to point to that new end of the line versus pointing to nothing at all. So what should we set it to? Be nice. It already was pointing to null. We were at the old end of the line. I don't know, some sort of end of the list. We found it. We checked next and it was already equal to null. Yeah, pointed to the new node we just created. And you may say, but Joe, this is some like variable inside this function, and it technically is. But the memory we've allocated for it is not on the stack. The memory we allocated is on this heap data structure. This variable named new node is not going to be valid once we're out of this function. But the memory we created for it is still there. So that pointer is still going to be valid after we're done with this function. Update it so that now what was the end of the list is now pointing to that new node, which is the current end of the list. The way I wrote this code, once we've done that, we're done. We could break, just return head. Hey, the head's still the same. We're appending something to the end of the list. We could also do insert, but I think to test this out, we probably have to get the print version of it working first. And again, as we're iterating through a list to print something, it's going to wind up looking kind of sort of like this. So we'll copy that code over, but then use our curses printing calls to actually print something corresponding to each node. So that for loop is going to be just like our I equals 0, I less than n, is how we're always accessing our arrays of size n. If we have a series of pointers pointed to in the beginning by head, and we have next pointers in a linked list, our loop is always going to kind of look like that. Start at the head, I++, right? Go to the next thing in the line, stop when there isn't anything next in the line, when we're at something kind of invalid. In this case, now that we've done so, we should now print out the node, right? We should do some kind of print information here. We probably need, because now, unlike with just printf, we have to be more careful with where we're printing things on the screen. So now it makes sense to have a row and a column variable. There's more appropriate ways to determine where to print something on the screen. There's functions that tell you how many rows and columns you have in total, so you can define what the actual middle of the screen is or the left-hand side. For now, we'll be 10 rows down and 2 columns across, so it's not kind of jammed at the very end. And we're just going to call some mv print w call. mv print w, row, column, and if nothing else, the value we're interested in. That looks terrible. Let's put some pipes around it. And then the actual value, which would be list iter value. And if we're going to do that, that's for a single value, we would want to add to the column, right? So print the first one at location 10, 2, the next one at 10, 12, the one after that at 10, 22. You may say, well, if you're not careful, you're printing an empty list, but this code already kind of takes that into account. If I pass null into this function, this for loop isn't going to ever execute. It's going to check list iterator is head. It's going to be equal to null. It's going to get out of that loop right away before it prints anything. I think I've scared you sufficiently, and that's good. That's our initially allocated random value in our linked list. I press A. That looks kind of good, right? Well, it's hard to tell exactly what's going on, but we're appending just arbitrary values to that list. If we so choose, we can make this printf look a little bit better, right? So I have a little box structure here. So let's do mv print w, and let's do like we did with the cards, right? You know, I very much enjoy making our printf statements look a little better. So let's make it a little box versus an actual value. On the next row, we would do 3 spaces, I guess, to match what we have for the integer. And if you want it to look a little bit better, you can kind of manually align what your printfs are going to look like there. That's always perfectly valid. If that's row plus 1, so print at row plus 1, print at row plus 2. It's like adding in those line breaks without really being required to add in those line breaks. That prints a nice little box. And then let's actually print out the pointer. Well, let's not print out the actual value of the pointer, but let's kind of visualize the fact that this is a linked list that has a little next pointer associated with it. And let's print it out. You know, it's a linked list, right? So let's print out a little arrow as well. You know how much I like fancy printf functions, fancy print functionality for data structures. Okay, so now we have a cool looking linked list kind of node here, right? Where there's the value and it's clear that there's a pointer, right? There's an arrow, it's a pointer, right? It's pointing to the next thing in the list. So now when I add my components here, you kind of get your linked list functionality. Now, curses isn't magical for you. If you pass in a value of row or column that's too high, it's just not going to look very good. So you do always have to be aware, certainly if you're building some interactive application, you have to be aware of how much space you actually have. And if you run out of space, it's not going to look good. It is also dependent on the amount of space you've given your application. So running it again now, you have more horizontal space here. You're probably going to be more limited in terms of vertical space. But now we can fit more things on our quote-unquote screen at one given time. It is pretty common practice, and if you're Pac-Man or whatever game, if you require 100 cross 80 number of characters for things to fit, you should call that function that checks the current resolution, and it should just exit if it doesn't have enough resolution. You can have a message that says, not enough space to execute this program, please create a larger terminal, and that's a perfectly valid way of doing it. I want to get to inserting things into the list. It's going to look very similar. The main difference would be that when we hit I, all we would really be doing would be checking the value and seeing if we're keeping things in sorted order here versus checking if we actually got to null here instead. But I think in the interest of time, we'll leave this here for now. And I'll very quickly on Monday kind of finish up the insert example, and then we'll kind of wash our hands with linked lists for the rest of the semester. Okay, good luck with Lab 8. Enjoy your weekend.